All right. Hello, everyone. My name is Daniel, and I was a summer intern with Globus Labs. My background is in astronomy, but over the summer, I worked on a integral field pipeline and learning how to apply parallel scripting within it. So to start, the specific type of data that I'm working with is called integral field spectroscopy, and it's a technique in observational astrophysics that is used to gather spatially resolved spectroscopic data from a target field at once, which means that you're enabling the study of spatially complex objects. Effectively, it's combining both photometry and spectroscopy into one observation. So to quickly go over the data format that I'm working with, there's of course the on-sky data, which is the actual science exposure and the integration time. Along with that, during the observation, you take some calibrations, which include a flat field, which help you understand where the location of the spectra on the detector is. Along with that, also the arc lamp, which gives you some emission lines to actually calibrate the data that you have. And the final data product is a data cube, which is basically just one file and it's a data cube. So that means that every single three-dimensional pixel, which is called spaxel in this type of work, and it's encoded with wavelength, but also location. And here's what some of these raw data formats look like. The on-sky data has some strong features, which are the sky emission lines coming from the ambient air glow of the atmosphere. But there's also some things like cosmic rays and stuff they have to get rid of during the data reduction. And then you can see the calibration files look similar because they're taken with the same instrument. Important takeaways from here are that each of the horizontal bands are different spectra, which means that each of the spectrums you see correspond to a different location in the target field. And that these are very small cutouts. So each of these data files, they have around 276 spectra. And with that, it has about a range of 2000 angstroms. So I'm going to talk about how parallelism was imputed to this pipeline with Parcel. And specifically, there's a bunch of levels of parallelism. So this instrument actually has two twin spectrographs, which means that the data is fed through two spectrographs and therefore to end up to two separate detectors. And those are combined at the end, but that could be parallelized. And there's also file groups that correspond to dithers. Dithers is a observing technique that's used to help basically increase resolution and also integration time by just basically doing the same observation, but shifting the telescope where it's pointing just a little bit. And then under that, there's also the individual files where sometimes in some of the steps, you're able to parallelize because with pre-processing, especially, it doesn't matter what order or there's no dependence between different files. And then finally, on an even smaller level, sometimes the spectra on the same file do not depend on one another, which means that that could also be parallelized. And here's a general overview of the workflow. The main steps are pre-processing, which then leads to calibration. And then finally, that all leads to the data cube creation. So what I show here on the left is the actual target field, and then what that integral field spectroscopy lattice looks like. And it basically splits into two of the spectrographs just by location, and those are added back to the final data cube at the end. And effectively, this workflow here, just on the top, is showing one dither, which includes a couple of on-sky exposures, but also the calibration data, the arc and the flat, which are all led to pre-processing, and then some other steps, and then finally calibration and data cube creation. And this is repeated for the different dithers, which means that's repeated at the same time in parallel until the final step where they'll all stack to the same data cube. And then on top of that, there's also that second spectrograph, which basically has the same thing repeated again. So to zoom in on one area, because I'm showing just the file level here, some of these steps I focused on trying to make even more efficient because it was a computationally intense task that basically would be a lot better if I parallelized on a grain lower than the actual files. So this is one example where I'm detecting the traces of the spectra. And effectively what happens here is I'm doing a bunch of multi-Gaussian fits, but the thing is that the multi-Gaussian fits do not really depend on one another, which means that I'm able to use Parcel to send out all of these optimizing tests in parallel, which leads to a much more efficient design. And then I'm also going to talk quickly about using Academy agents, which basically is a optimizer agent with internal state, which helps get the actual cosmic ray detection done. So that's this part of the pipeline. And there's going to be another talk about this later, but basically Academy, what I'm using it for is having an internal state agent for each of these spectrographs. And that allows for me to do optimizations that are informed on the instrumentals. So basically cosmic rays are just these little obstructions in the data, and the goal is to detect them. You could see on the top right here, I show like a couple different cutouts of the data. And over time, you can see the cosmic rays, they're random. But on top of that, also the instrument, it's kind of hard to see because it's subpixel, but the actual data shifts a little bit. And in order to get these, to get the cosmic rays abnormalities, I have to get the residual between two different similar images. And because I want to do the best job that I can, I often have to figure out that shift that's happening. So effectively, the cosmic ray agent that Academy has, it's initialized in the beginning of the pipeline. And for each of the different twin spectrographs, it effectively uses the internal state of the actual observation. And it's able to compute vertical shift and horizontal shift. You could see on this graph here that there's like a trend. It's not random, which means that there are instrumentals, for example, the temperature of the actual spectrograph, that cause optical distortions and effectively result in these first order shifts. And the same thing happens for the other spectrograph. So now to get into the evaluation, so I was able to run this pipeline on Midway at UChicago on CPU nodes. And with just one node, it was around 6 hours or 7 hours actually. And with 32 nodes, it got down to about 25 minutes. So a big increase in time. And a breakdown of the workflow, you could see that data cleaning is a pretty small step, but then the flat plate trace detection, which is that multi-Gauss optimization, took a while. And then cosmic ray detection runs in at the same time as that because there's no dependencies there, which then lead to the calibrations and data cube creation. This is on 16 nodes. That graph looks a little bit different for different nodes. But the conclusion is that with this pipeline, I have scalable, informed, and accurate data processing, which then can lead to the idea of an adaptive approach to target selection and processing during a given observing night, which then just optimizes the discovery in any field of astronomy. So I'm going to end with just this image here. This is an actual scientific result of this pipeline. So here I'm just showing that at Lyman alpha for this specific lens galaxy, there is actually a very strong emission, which indicates that there is very high star formation in this very early type galaxy at a very far distance. All right, thank you.